Hi everyone, welcome back. In the previous episode I talked about sampling distributions, and I said that sampling distributions and the Central Limit Theorem are two ingredients that go together to help us do research with samples to understand populations better. In other words, to do inferential statistics, which require assessments about probability. What's the likelihood of certain things happening? In this episode, I'm going to say a few things about the central limit theorem. Now, it's a complicated, it's a theorem, and mathematical theorems tend to be a little bit complex, but I'm going to tell you just the tiny little things that we need to know about it in order for it to make sense. So, again, last time I talked about sampling distributions and how they were made up of all of the a theoretical sampling distribution is made up of all of the possible unique sample means that we could get if we had the means, the time, the resources, and whatever, to go out and actually get every single possible unique sample from a population for a given sample size. So the thing theoretically does exist, but it in practicality does never exist except in computer simulations. But still, it's out there, and the fact that it's out there is good because it's something that we need and something that we can use. So anyway, let me try to explain what the central limit theorem means and what it has to do with sampling distributions and this process of doing research in inferential statistics. So the two things, and it's really one and a half things that are all we really need to know as social researchers about the central limit theorem. Okay? One, if the sample size that we're using is big enough, if it's sufficiently large, the shape of the resulting theoretical sampling distribution will be normal. Now, that begs the question, what is big enough? What is sufficiently large? And I don't have a firm number to give you. There's rules of thumb, but they're just as often invalid as they maybe are valid. The quickest way for me to define what's a big enough sample is you know it when you see it. Okay, but anyway, the two numbers that pop into my head are very small numbers. But seriously, anytime you have 10 or fewer participants in a condition, let's say you have a control group and an experimental group, and you have two different sets of people in each of those two groups. If you've got less than 10 people in those groups, you're definitely on very thin ice in trying to make some valid statements about the findings that you get from them. So 10 is one very, very shaky, minimal rule of thumb number that we could say is is not sufficiently large. Another number that pops into my head, maybe I don't have any evidence to back this one up, is actually not a firm number, but about 30. If you have about 30 participants in each of those two conditions, or as many conditions as you are using, that ought to be pretty good. You're getting them to be on pretty solid ground. But it's all relative. If you're doing research on national trends, let's say you're doing a national survey, you're polling to see which presidential candidate people prefer in a major election. I think you'll agree with me that if you read a survey result that surveyed 30, even 30 people from across the nation, I think you'd agree with me that you'd probably wonder how representative 30 are of almost 300 million voters, or however many voters we have, 200 million, hundreds of millions of voters. I think you'd be skeptical of 30 or even 300. So sample size is relative to the question and the research project in mind. So anyway, I'm going to leave it kind of vague like that. If you have a big enough sample size for this situation, the resulting sampling distribution, and it's usually a theoretical thing, will be normal. And now already I hope that that triggers some sense of recognition in your mind, some sense of familiarity, some sense of, oh, that sounds good. If the distribution is normal, I hope you think that's good, because you know normal curves now. You know how to use them. You know the probabilities associated with them. So you know that if you have a situation where you or a group is out in the tails of one of these suckers instead of towards the middle, you know intuitively, if not more than intuitively, that that's a interesting place for that group or to be, or that person to be, or in this case that group, that sample to be. Okay, so that's a good thing. If the sample size is big enough, this sucker will become normal. All right, so the second statement is really maybe statement 1.5, and that is that anything that you do to jack up, to increase your sample size, the larger the sample size gets, the shape of this distribution, of the sampling distribution, will become even more normal. What do I mean by more normal? It will become more leptokurtic. It will become more taller and skinnier. It will become more scrunchy. All right? Now I want to make something very clear. When I say that when you increase the sample size, I am not saying that you increase the number of samples. All right? I'm not talking about increasing the number of samples. I'm saying use a bigger sample size in your research. Okay? If you had 10 people in your control group and you move it up to 20, or you move it up to 40, or something larger, the theoretical resulting sampling distribution in the theoretical background is going to be taller and skinnier, more normal and taller and skinnier. Okay? Look at these two pictures. You might have a sampling distribution represented by this width of a curve, this height and width of a curve, with a smaller n, whatever I mean by smaller n. If you increase that sample size, say this is 20, increase it to 40, it will get taller and skinnier still. Okay? So again, increasing the sample size is not meaning increasing the number of samples. In all situations here, we're pretending or assuming that all of the possible samples for that given sample size are already in. They're already in the pile. All right? A sampling distribution is a pile of means. And so, again, it's a pile of all possible means that you could get, all of the unique means, all of the unique groups that you could get for a particular sample size. So as the sample size increases, this thing gets taller and skinnier. Those are the two givens of the Central Limit Theorem. That's what that theorem mathematically expresses to us. It says more, much more. And in statistics, in true mathematical statistics, you might be interested in getting much more into this and in mathematics. But for us psychology researchers, that's pretty much all we need to know about the Central Limit Theorem. So it's not nearly as scary as it sounds, is it? Okay, now, what does it have to do with things like the standard error of the mean? So last time, in the sampling distributions video, I talked about I introduced the standard error of the mean. So as previously discussed there, the distribution will have a mean of means. A sampling distribution has a mean of means. All of those means collectively have a mean that we call the mean of means. All right? And that mean of means will always be equal to whatever the raw score population mean is. So that's a good thing. All right? So the thing has a sampling distribution has a mean of means, and all of those means have a standard deviation. Okay, you could calculate the standard deviation of all of those means. Regrettably, we don't call it the standard deviation of the means. That's what we've named the standard error of the means, or sometimes just the standard error. All right, now again, in real life, you don't go out there and get every possible sample, and you don't get their mean. So you wouldn't be able to calculate this standard error for real. Instead, we have that wonderful little formula that I introduced last time. This is our E equals MC squared in social research. Okay? if you know this population standard deviation, and of course you know the sample size, that's thoroughly in your control. If you're going to do research, you say, I'm going to use a sample size of 20 or 50 or 100 or whatever, you get to decide that. All right, so whatever the population standard deviation is divided by the square root of the sample size you're using is a really good estimate of the true standard error of the mean. It's a really good estimate of the real, honest standard error of the mean, which means that we don't have to go out and get it. So we couldn't get it in the first place, and now we're totally relieved of that burden and that responsibility that we wouldn't ever be able to fill anyway. So this is wonderful. It's true for virtually all populations, no matter what the population's raw score distribution shape is, whether it's skewed, bimodal, multimodal, rectangular, any crazy shape whatsoever, the central limit theorem kicks in. So this is opening the door for us to use any kind of interval ratio scale variable. I'm talking about interval ratio scale variables exclusively when I talk about all this, by the way. It opens the door for us to use any of them. Any of them. If our sample size is big enough, it doesn't matter what they look like in the raw population, what the raw scores look like. It doesn't matter if they're skewed, if they're flat, if they're any shape. If we're using a big enough sample size, the sampling distribution that we're going to refer to will be normal. That's beautiful. That's wonderful. I want to demonstrate that to you here using a tutorial that's out there on the web. Okay, it's got this god-awful web address. You can copy that and go play with this yourself if you wish. Let me open it up. I've got it opened up here, so let's put it right here. Okay. All right, now this is a really old tutorial. It's not really high-tech graphics or anything like that, as you'll see. But it does a wonderful job of demonstrating live. We can see the central limit theorem in action. All right, so I'm making the case. I'm making the claim. We're going to court. This is evidence, all right? I'm making the claim to the court that the central limit theorem will work to give me a normal distribution, a normal sampling distribution if my sample size is big enough for any circumstance. So this tutorial starts out, the default is to start out with a population that is already normal, okay? So things like intelligence, things like stress. Stress is probably normally distributed in the population. Creativity probably is. Anxiety, happiness, all kinds of things are normally distributed in the population, okay? If we're talking about an interval ratio scale measurement way of measuring it, okay? All right, this isn't going to work for me to talk about with his intelligence because the numbers don't match up here, okay? So on your screen, I hope you can see this. I know these numbers are very, very small. But this default population, I can't control these parameters. So this population has some parameters. Let me read them to you if you can't see them. The mean of this population is 16 units. Okay? I'm going to keep it abstract. I don't even know what the example could be. All right? So whatever this variable is, it's got a mean of 16. And it's symmetrical and perfect. So the mean, the median, the mode are all right down there in the middle at 16 each. Okay, it has a population standard deviation of 5 units. Okay, all right. Now again, the central limit theorem says that the sampling distribution, which is going to get built right here, we're going to sample this population one at a time. We're going to take a sample out of the population of given sample sizes one at a time, and we'll drop them down and we'll see them first in this panel here, and we'll see what the sample data looks like, and then the machine will calculate the mean of that group and drop it down here and start building a sampling distribution. So it's called the distribution of means here. We've been calling it the sampling distribution of means. Okay, that's going to get built right here. So let's start with the defaults, everything on default here when you open up this tutorial. Okay, so what do we have? We're going to start with a really, really small sample size. Sample of 5, okay? N is 5. That's ridiculously small. You would never do research with a sample size that low. Good, serious research. So if we have a normal distribution and we sample 5 people, here we go. Here comes 5 people. Watch this. It's really fun. 1, 2, 3, 4, 5. There comes 5 people, and the computer calculates the mean of those 5 people. So there's the sample of 5 people and their scores that fell out of the sky like manna. And it calculates their mean and blunk drops it down here. Okay, so we have the first mean of this sampling distribution. Okay, and thus far that mean was 17.92. Again, the population had a mean of 16, so these scores were just ever so slightly higher on average than the population mean, okay? Approximately 18, whereas the mean of the population was 16. There's no, this thing was also a little bit clunky, this tutorial, and I didn't create it. I apologize on behalf of it. It says standard deviation down here, and of course, as we've just learned, that is truly the standard error. That should probably say standard SE for standard error. But I like that it says standard deviation just fine, because the standard error is just a standard deviation, okay? I really want that point to be clear. So it's okay that it's calling it a standard deviation here. All right, you can't have a standard deviation of when you have just one value, so there's no standard deviation yet. How much does that differ from anything? It doesn't differ, there's nothing to differ from, so it's only one. Okay, we got the first teaspoon of water out of the ocean, okay? A sampling there's bajillion samples of 5 at a time. This is a really big population. We don't have a sample, we don't know the population size here, but let's just pretend it's all humans. This is the pile of all people on whatever variable this is, all 6 or 7 billion people on planet Earth, okay? How many unique groups of 5 at a time are there in planet Earth? Oh my God. Almost infinite. It might as well be infinite. There's so many, okay? So we just took the first little teaspoon of water out of the ocean, and there it is. Okay, enough about that. Let's watch another one. Here comes sample number 2. That one will go away, and here comes the other one, and there comes their mean dropping down, okay? All right, so now we have 2 means, and you see, okay, that one's a little bit lower, and this thing is now calculating the mean of those means, and that should also say mean of means here. So the mean of means now is already really close to the population mean. I keep saying that the mean of means will be a dead ringer for the population mean. Mu x bar will equal mu. All right, this is mu up here. This is mu x bar. With just 2 samples out of the whole ocean of teaspoons of samples, I've got a pretty good estimate of the population mean already, okay? The standard error of the mean is represented there, okay? I'm going to do a quick calculation real fast so that as we build this thing, let's make a prediction of what that standard error should be. We can make a clear prediction of what the mean of means will be. The mean of means, as I've just been saying, should be 16, all right? When we do this over and over again, it should settle in on a number that's about 16. What should the standard error be? Well, we can use our wonderful little formula to calculate that. And so our population standard deviation is given right up here of 5 units, okay? So it's 5 divided by the square root of n. So 5 divided by 5 square root, okay, is equal to, I'll round that to 2 decimal places, 2.24, all right? 2.24. Our standard error of the mean as this thing proceeds should get closer and closer to, I just say 2.24, okay? With just 2 values, it's not very close. It's 1.59, but who cares? It's like, you know, does your little puddle of 2 tablespoons of water look like the ocean yet? Hells no. Let's proceed. Here comes sample number 3. 1, 2, 3, 4, 5 more people, and there comes their mean, and boom, it's just pretty much like the other mean that was just before it, okay? So now we got 2 means, still really close. Standard error, don't worry about yet, okay? Here comes here comes our 4th group, 5th group. Ooh, that one's a little bit lower. We got some low scoring people in that sample. See how, see we got 3 pretty low scores. Almost, this one's almost getting, kind of almost in that rare territory. Kind of rare to get somebody that low on whatever this thing is. Okay, so it pulled, and 2 others that are kind of on the low side. So anyway, just pull, let's just make note of this as we see it. Okay, all right. What have I got? I got 5 samples so far. Here comes 5 more. I'm not going to do this for an infinitely long period of time. Don't worry. Let's go up to 10. All right. Here comes the, where are we? 7th. Here comes the 8th group. Oh, look at that. Look at that. We got a rare high scorer here on whatever this variable is. Look at that. It fell right out of the very top end of this thing. That's really unlikely to get somebody like that. And they pulled their mean up quite a bit. 4 other people that are pretty standard, they're close to the middle, and 1 almost outlier. Really high score up there. Okay, that's 8 samples. 9, 10. I've got 10 samples so far. All right. Now, what's my mean of means? My mean of means is 16.05. Getting real close to what I predicted. It should be 16. My standard error of the mean thus far is 2.29, and I said it should be 2.24. Real close already. And that's only 10. 10. This is a tiny palm full of water out of the ocean, okay? All of the samples of 5 at a time that I could get from the whole population of 7 billion people. I mean, we got a long way to go here. Get comfortable. If I do this one at a time, we're going to be here a long, long time, okay? All right, I'm not going to be here for a long, long time. We can speed this up. Speeding it up takes the fun out of it, so we're not going to be able to see them come down anymore. But here comes 1,000 samples. So, wow, so fast you couldn't even see it. The computer went and did 1,000 groups of 5, calculated their mean, and dropped them down there for us in an instant. Okay, so we now have 1,010 samples there. My mean is 15.93, real close to 16. Look at my standard error. It's already at 2.24. It's already 2 point. Now, 1,000 is a lot, but that's still nothing. That's still nothing. Okay? So let's go get 10,000 more. Okay, there's 10,000. Here's 10,000 more. So we got 21,000, 30, 40, 50, 60. So I'm going to go up to 100,000. A little over. Okay, we got 101,010 samples here in our pile here. That's a pretty good number here. Now, can you see how in real life I wouldn't dream of going out and getting 100,000 samples of 5 people. Oh my God, what a tragedy. But anyway, what do you see here? What does that shape look like to you? I'll give you a little clue here. I'm going to click this fit normal curve over it. And you can't even see the normal curve. It fits so perfectly. All right? My mean is just about dead on, 16.01. Okay, trust me, if I keep hitting 10,000, it's going to stop at 10,000. It's going to stop at 16. All right? Don't make me prove this. 16.01. Okay? My standard error has already long ago settled in on what its value should be, 2.24. And trust me, it will eventually get to 16 exactly on the head. All right? We're, perhaps less than a hundredth of a point away from that right now. Okay? It's being really stubborn, but trust me. All right? I'm already, I'm getting close to, I got over 300,000 there. It finally stopped at 16. Okay? So I got 300,000 samples there. All right, so the central limit theorem said that if the sample size was big enough, the resulting sampling distribution would have a normal shape. Now, it might not surprise you to be able to get a normal shape out of a normal shape. Indeed, that's maybe not terribly surprising. But what's kind of neat here is that it worked for a sample of just 5 at a time. And I keep saying 5 is a ridiculously small sample size. Okay? So the central limit theorem is pretty powerful. Even if you're foolish enough to use samples of 5, if you're starting with a normal distribution, you can get a normal distribution, sampling distribution. All right. So it worked. Now the second statement of the central limit theorem said that if you boost up the sample size, the resulting sampling distribution should be taller and skinnier. So unfortunately I can't keep that on the screen here, so I want you to kind of burn that in your memory what that looks like, okay? The width, the height and width of that sampling distribution there. Because now I want to change the sample size to, let's double it, let's go up to 10. Okay, there it's gone. Now here comes the first 10 participants and their mean, and you know this process now, so let me jump right to 10,000. Here comes 10,000 of them, and look at the shape, okay? The mean of means is already 16. I've only got 30,000, and that's 30,000 sounds like a big number, but again, that's nothing. All right, I'd have to recalculate what the standard error should be because it changed. My sample size changed, so it's still 5 divided by the square root of n, which is now 10. So the square root of 10. So 5 divided by the square root of 10 is 1.58. And my standard error is 1.58. The machine already has it. Okay? And as you can see, it's a normal curve. Now, hopefully you remember what the last one looked like. It was kind of like this one over here. All right? Okay? It was taller. It's now taller and skinnier, just like the theorem predicted. All right? So the theorem's so far, 2 for 2. All right? 2 for 2. Let's boost this up. Let's go. You can choose different sample sizes. The biggest sample size this tutorial lets me do is 25. So here comes 25. Okay, we could watch 25 people get drawn from the population one at a time. And here comes their mean. Sooner or later, plunk, there's their mean. Okay, let's go get 10,000 of those and see how it's taller and skinnier. All right, the mean of means with just one click is already at just 16.01. My standard error now should be 5 divided by the square root of 25, which is 5 divided by 5. I don't need my calculator. 5 divided by 5 is 1. All right? I'm at a standard error of 0.99, which is my first 10,000. Okay? I have a standard error already of 1. My population mean is right at 16. Okay? So taller and skinnier still. So 3 for 3. The central limit theorem said that the sampling distribution would get taller and skinnier with each increase in sample size. Okay, now maybe none of that was shocking that we could get that out of a variable that was already normally distributed up there in the real world, in the real population, in the raw score population. So this tutorial lets me change that. So I can choose different things here, okay? So let's try the next one, okay? Now that population has become flat. It's flat. It's every variable is equally likely as every other variable. Okay. I can't even think of a good I can't even think of a good psychology example of anything that's just absolutely flat. Okay. But I can think of mathematical ones like the digits in your telephone number. Okay. Take the 4th digit in your phone number. Anyone's phone number. The 5th digit, the 7th digit, whatever digit you want. Okay. There's no pattern there. Any number is just as equally likely 0 through 9 as any other number. Okay, so it's just absolutely flat. All right, so we still have a population mean of 16 units of whatever this variable is, and we have a new standard deviation. It's an awkward number, 9.52. And let me go back down to well, let's just leave it there. We'll use a sample size of 25, okay? If you have a sufficiently big sample size. I'm picking the biggest sample size this tutorial will let me. What will happen here? Now, the central limit theorem predicts that I should have a normal distribution in my sampling distribution down here once I roll, okay? So that's the prediction, that it should center around the mean. The mean of means should be equal to this mean. It should be 16 right below it. And my standard error should be whatever my standard error should be. 9.52 divided by the square root of 25 is 5. I should have 1.90, okay? So my prediction is a normal looking curve with a mean of 16 and a standard error of 1.90. Here comes, I like to show you one. Here comes one of them, okay? People coming from all over the place, all right? 25 randomly selected scores, and there's their mean. Let's get a whole bunch more. Here comes 10,000. Whap. And ladies and gentlemen, that looks like a normal curve already with just 10,000 samples. I said this should have a mean of 16. It's at 16. I said it should have a standard error of 1.90, 1.89. Okay, and I'm confident that if I keep clicking this and add to it, there, it's already reached 1.90 with a mean and means of 16. Okay, normal curve out of a rectangular one. Okay, so that means that I can do my statistics with that in mind instead of this in mind. It doesn't matter that the variable is flatly distributed in the population. I'm now not interested in individuals. I'm talking about samples. So if I have an experimental group that has one of these means way up here in this high end here, and I've done something, I've given them some treatment that should have made their score higher. You know, I hypothesize that this would go higher. I can tell you the probability of that happening. So I can take any one of the any sample under the curve. I can take any mean under the curve, use my z-score tables and z-score formula, and tell you what percentile that mean is associated with. And if it's a very, very high percentile or a very, very rare low percentile, I can compare, well, gee, I was not expecting that. I was, you know, if the treatment didn't work, it should have landed somewhere in the middle, and wow, I'm way out here in the tail, out here in the rare part. That's inferential statistics in a nutshell. All right, so I think that was about my fourth. I think I'm 4 for 4 here with demonstrating the central limit theorem. Okay. How well is the central limit theorem going to work with small samples when we have this thing? Let's try that. I'm going to go down to 5. All right. What if I was foolish enough to use samples of 5 from a population like this? Would it work? And you tell me. See how it's we have a much wider normal distribution now, but it's normal, all right? That central limit theorem kicked in and it's working for a sample size of just 5 with this crazy population variable that's just flat. That's marvelous, okay? Gosh. What about 2? If I was so dumb as to use samples of 2, I'm going to go out and do sample sizes of 2. I'm going to get 2 people. Look at that. This is getting kind of more pyramidal, you know, more of a pyramid than a normal curve. Okay, so it's the central limit theorem. Bless its heart, it's trying its hardest to accommodate. So it's kind of falling apart with samples of just 2. Okay, kind of more pyramid than normally distributed. All right, so you'd be off on a fool's errand if you were going to use sample sizes of 2 anyway. All right, let's move on to another population. How about something that's very skewed? Reaction times are very skewed, okay? People will respond, most people respond very quick to a tone or a visual stimulus or whatever, and a few people are slower and some are slower still, and so this thing, you know, the very slow pokes, the comatose people are pulling the tail of this thing off in a positive direction. We have a severely positively skewed distribution here. Will the central limit theorem work for that? Let's do something modest, okay? Let's use 10. Sample size of 10, all right? Tell you what, let's be really bold. Let's be foolish and do 5. Sample sizes of 5. The central limit theorem is not going to make a prediction about 5. No promises with 5. 5's that's too small. Does it work with 5? Let's take a look. Now notice something. Where's my mean of means going to be? My mean of means now has dropped. It's no longer 16. It's an awkward 8.08 on here underneath this blue line. So my prediction, the central limit theorem predicts that we should have a maybe approaching normal curve right underneath this mean of 8 with a standard error of whatever it would be. We could calculate it, but I'm not going to bother. All right, so here comes a bunch. Okay, now look what's happening here. My mean is doing well. I don't worry about the mean. The mean of means is always a good dead ringer. I'm already there, 8.09. It's going to settle in on 8.08. I'm confident, pretty confident. Okay, close enough. But look I can see that the normal curve in the background is, this thing is, it's still a little bit skewed, all right? still a little bit skewed. You can see it's kind of bulging over here on this left side, and you can see exposed a little bit of the normal curve, that the perfect normal curve behind it. So like the population values up here, they're kind of heaped over here on the left. The sampling distribution is a little bit heaped over here on the left. So the central limit theorem didn't make good on its it made no promises for sample sizes of just 5. But it said if the sample size is big enough, it'll work. Well, let's try the biggest sample we can. Will 25 work to cure this problem when we have a severely skewed population? Boom. Yes, it does. All right? That thing is well within the normal curve. Nice, tall, skinny, normal distribution. All right? So it works. It works with severely skewed data, severely skewed population values. All right? Okay. Let's move on. The last kind of population is up to me. It lets you build a custom one. It lets you build a custom one. All right? So we talked about bimodal distribution. So I'm going to make a very pronounced bimodal distribution there. Okay, so there's a population which is very visibly bimodally distributed. Now in real life in psychology, I can't think of any good variables that are this sort of discrete, okay, this distinct, male-female stuff, right? The difference between males and like if this was weight, okay? Now males tend to be heavier, so this bulge might be the males with their heavier weights, and females tend to be smaller and lighter, but it's not this pronounced. We don't have this distinct of a normal bimodal distribution in real life, okay? There's so much more overlap. So but what if we had something that was pretty severely bimodal? This is more bimodal than you'd probably ever see in real life. All right? And let's see if it works. Let's just jump right to the wise thing and use a nice big sample size of 25. So here comes my samples of 25. And look at that. I have a nice leptokurtic normal sampling distribution with all the correct parameters for this crazy bimodal distribution. So the central limit theorem works for every population that I've seen so far. I'm going to end this with the absolute craziest bimodal thing I could make. All right? Our world is becoming, our political culture is becoming so severely divided that we have it doesn't matter which end I put things. We have Republicans over here on something, and we have Democrats over here on something. Okay? I don't know what this is. Attitudes or beliefs about something or another. Okay? And then sometimes feeling like this is the case here, that people are so severely divided that nobody's in the middle. All right? So literally, for this pretend population variable I'm creating here, people are absolutely divided. There's a little bit of variability among them and a little bit of variability among them, but nobody in between. Nobody in the middle ground here. Okay? Could the central limit theorem work for us with this crazy population variable? All right? And let's just be really silly and start with a sample size of 2 for this one, okay? So you're going to start with a sample size. You're going to do research with a sample of 2? Yeah, you're really dumb. Okay? Well, what do we see here? If you're sampling 2 at a time, I'll tell you what I predict. I predict that, hey, one scenario might be both people come out of this population. Another might be both come out of this population. And a third scenario is 1 from each. So I'm imagining numbers dropping down, say 1 from each, both from one, both from the other, and again 1 from each. Okay, so they're falling in 3 locations. My means are gonna. Let's see what happens here. Let's do 1 at a time. Okay, so there I got 2 from the upper end, 2 from the Democratic pile, right? There's 1 from each pile. I got 1 Democrat, 1 Republican, and then it calculated the mean and dropped it right here in no person's land, okay? Right in the middle. Okay, here comes the third group. 2 more from the Democrats, dropping their mean down over here. And there, we have 2 Republicans and their mean of those 2 people down there, okay? So can you kind of predict that that's what's going to happen here? We're going to have a little cluster of means if they're both Republicans, and if they're both Democrats, they'll pile up over here, and when there's one of each, they'll pile up in the middle here, okay? So, there, look what's happening, okay? Now, the central limit theorem was hoping to give us a single unified normal distribution there in the middle. But I want you to notice something here. Obviously it hasn't done that. It's creating 3 piles just like I got you to imagine. Okay? But I want you to notice something. If you look at those little 3 piles, you got to give the central limit theorem a little bit of credit, because look what it's trying its best to do. It's saying, well, I can't give you one nice normal distribution, but I'll give you 3 nice little normal distributions. So it's nicely packing up 3 little piles in normal curves. That's not quite what we're looking for, but I gotta give the CLT a little shout out for working its little heart out to try to give me normal curves here. Okay, so anyway, doing research with 2 at a time is always foolish. But is there hope if we're going to be wise and use a big sample size? Okay, so now let's try samples of 25 and let's see what happens. Can it work? Can it fix this insurmountable divide between Republicans and Democrats in this survey or this poll or whatever we're doing here? Can it bridge the divide? Here comes 10,000, and look what happens. We have a perfect normal sampling distribution being created right before our eyes. The central limit theorem is gorgeous. It works every time if you have a sample size big enough. So the statement rings true. If your sample size is big enough, and hey, 25 ain't exactly a giantly big sample size. Now, if you're going to go do your research project on your own in your next class, getting a sample of 25 in a control group and 25 in an experimental group, for example, might feel, oh my God, I got to find 50 people. That's a lot of people, but it ain't exactly huge research, okay? But it's as big as this tutorial goes, and it was big enough, okay? I get a normal distribution, and I'm trusting it that if I calculate the parameters, they'll be correct. I can see that the mean of means is already perfect, 15.2 for each, and I predict that the standard error is dead on, or will be if I keep clicking. So there we go. The central limit theorem works for every population I've given you, so long as you're using a big enough sample size. In a couple of cases it fell apart when we were dumb enough to use samples of 2 or 5, but as long as you're using sufficiently big samples, it works. So if you're really interested in this tutorial and want to play with it yourself, by all means jot down this god-awful web address and go give it a try yourself. So there you go. That's my central limit theorem demonstration. Okay, so because of the central limit theorem, we are confident that we can answer questions about sample means in the same manner that we could answer questions about individual scores, because now they assure us that we have normal curves in the background to play with. All right, and we know how to use z-scores, we know how to use our z-table, put those together, and we can answer questions about percentile. I can tell you how rare or non-rare a sample is just as easily as I can for a individual. All right, and I can go backward as well. I could find out what would be a rare sample needed. What mean would I need to be? How high should it be for me to be considering that it's out there in the rare zone, in that less than 0.05 area? Okay, so it works backwards as well. So we're dealing with a normal curve here. We can standardize the sample means almost precisely the same way as we did with z-scores, and perhaps in another episode I'll demonstrate just that for you. Okay, so I hope that wasn't too painful. That's the central limit theorem. Again, just 2 statements, really 1.5. If the sample size is big enough, the resulting sampling distribution should approach normal, and anything you do to jack up that sample size will only serve to make that thing even more normal, taller and skinnier, more perfect. Okay? Central limit theorem. Know it, love it, It's why we can do research. Sampling distributions and central limit theorem. Love it. Bye-bye.